All right, so let's go and look at the last lecture. That was on 16 December, the lecture number 10. We had a suggestion of sets, and we said this has a certain property. Namely, it's exactly like quotient by the equivalence relation. Equivalence relation is induced by that surjection itself. For surjective group homomorphism, similar things happen. But in topology, a surjection is not enough. You need that to have quotient topology, and then it has that nice property. So those were the quotient maps. Earlier we had talked of similar things for embeddings, and yesterday we talked about whether some properties are inherited by subspaces or embeddings and quotient spaces or quotients. Hausdorffness. So we concluded by two different arguments, one very pictorial, other completely general, that Hausdorffness is inherited by topical subspaces. Then we talked about quotients. And we talked about quotient modulo and equivalence relation. And equivalence relation can be alternatively described by its graph. So I might write it as tilde, I might write it as R. And the question was, when is the quotient Hausdorff? The answer we found had nothing to do with whether X is Hausdorff. The answer simply turned out to be this quotient is Hausdorff if the equivalence relation is closed in X cross X. Then I gave you an example of an equivalence relation which was not closed in X cross X. So naturally the quotient is not Hausdorff. I told you that given any infinite sequence in this dotted arrow, both 1/4 and 3/4 are going to be its limit points. I heard you guys think that I am giving you no exercises. I am giving you plenty of exercises. Everything that I am not verifying here is an exercise. Do you understand? Saibal, do you understand? Saibal, are you there? Makran, are you there?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Yes. So what are the exercises that I give? Everything that I don't prove to the last detail is an exercise.
Okay, sir. Okay, sir.
Huh?
Okay.
So this should have been an exercise. I could have written here exercise, but it's for the tutors to detect that, oh, no proof is given of this in the class. Now you guys give a proof, and you have to demand a proof from the students in the tutorial session. So for example, demand that both 1/4 and 3/4 is the limit of any infinite sequence in this interval. Take any infinite sequence between 1/4 and 3/4, and now show that both 1/4 and 3/4 are its limits. For example, it may be the constant sequence 1/2, 1/2, 1/2, 1/2, 1/2. Then it will have both this and this as limit. Because in the quotient, this whole open interval is going to be a single point, and 1/4 and 3/4 are going to be its limits points of a single point. That point is not closed. Okay. So we wrote it as a theorem to emphasize this point. And now we come to today. And so once again, I ask you any questions on yesterday's material. Otherwise, I'm starting on a new topic called Topical Course. Yeah, should I continue? Okay, thank you. I take silence as yes, or I'll interpret silence whichever way I want to. Because after giving you a chance to say something, if you don't reply, then I will choose the reply. Okay. So the idea is this. You know that an abstract group this is a set and this is a binary operation. Okay. This is a set and this is a binary operation, which means it's a map from G cross G to G called multiplication. Now the other kind of thing is a topological space. This is a set and this is a set of subsets of X, meaning T is a subset of the power set of X, which means any member of T is a subset of X, any way you like to see. Now we come to a combination. Now here, of course, there are three properties, 1, 2, 3, group actions. 1, 2, 3. Okay. Here there are various conditions such that the empty set belongs to T, all of X belongs to T, closed under arbitrary unions and finite intersections, closed under finite intersections. So now finally we combine these two together and have something called a topological group. It's not called groupical topology. Topical topological space. No, it's called topological. So it's a set, a group operation, and a topology. Set is a binary map from G cross G to G, and this is a subset of power set of G, such that first condition, G dot is an abstract. See, up to now you only called it a group, but now that we are studying topical groups, those things which you earlier studied are called abstract groups. Second condition is GT is a topological space. And the third condition is that and T are compatible. So what does that mean? It simply means that the group operations are continuous. So this means the following. This from G cross G to G is continuous. The second condition is the inverse map X goes to X inverse is continuous. Multiplication inverse identity map, of course, is continuous. Yeah, all constant maps are continuous. So this is what makes a group a topological group. Its group multiplication should be continuous and its inverse should be continuous. So is it clear to you what is a topological group?
Yes, sir.
To show that it is clear to you, give me an example.
Sir, real numbers as additive group and with usual topology.
Wonderful. That's a great example, but I'm going to begin in the usual general style. Okay. So I'll say that to every abstract group, we associate a topical group. How? G to this, you associate, this association is shown by a wavy arrow. G dot and discrete topology. Because we know that in the discrete topology, if G has a discrete topology, G cross G also has discrete topology. And once you have discrete topology, all maps are continuous. And so this is a topical group. So all abstract groups are special cases of topological groups. Therefore, what we are going to study is now something more general than group theory. And all group theory is a special case of topical groups. Yeah. Already you know lots and lots of examples of topological groups. All the examples of groups you know are discrete topological groups. Okay. Next, let's take the example which our friend gave us, which is R plus and usual topology. So this is a topical group because we have last quarter lecture, I had asked you to prove that this map x comma y goes to x plus y is continuous. And you had proved it in tutorials or whatever. Also, the map R to R, x goes to minus x is continuous. So we have fulfilled the definition of a topical group. Okay. Can you give me some more examples of topical groups?
Sir, GLNR.
GLNR. Somebody is giving me GLNR. But before that, let me look at GL1R. So let us take the multiplicative group of R. Probably you are used to writing it with some star or something. Okay. This is R minus 0. And the operation is x, y. Okay. This is the multiplication. And usual topology, meaning as subspace of R. So one of the exercises for you was that this map maps to xy is continuous. But I want this subspace. So I have this R multiplicative cross R multiplicative, R star as you call it. I keep forgetting. This is a subspace of that. And this is a subspace of that. And under multiplication, this goes here. Now, why is this continuous? Because of the universal property of embedding. This is an embedding. So, because whenever two numbers are non-zero, their product is non-zero. This composite map, which is continuous because inclusion is continuous and this is continuous. So, composite of continuous is continuous because it's a category. And this factors via the image of this because the image consists of non-zero elements. Therefore, this map is continuous. This is continuous by all that we said in the last lecture and the lecture before last lecture. That's why this map is continuous. Okay. Therefore, and the other map was, this was again a separate exercise given to you that the map from here to here, x goes to 1 upon x is continuous. So this shows that this is a topological group, this one. Multiplication, and usual topology. Okay, so before coming to your example of GLN, which was also nice, I want to make this into a category. So let's change the color because I am changing the topic. Category of all topological groups. Okay, this is my category. I call it top groups. What are its objects? What's going to be the objects of the category of topical groups? All topological groups. Yeah, any question?
No, sir.
And what are the arrows? Now you see,
So the
yeah,
group homomorphisms from groups which are also continuous.
wonderful. This is the correct answer. So if I have topological group G dot and T, and from here I want to go to G prime dot prime T prime, that will mean a map F from G to G prime of the underlying sets such that one F is a group homomorphism from G dot to G prime dot prime, because these are groups. And the second condition on it is F is a continuous map from GT to G prime T prime. Now, because I'm not going to verify it, I'll call it an exercise so the tutors will have enough raw material. Exercise. Define composition in the obvious way. Okay. Define composition in the composition on underlying sets. Just compose the sets map. Show associative. Show composite is again a group. So show that composite is again an arrow. Of course, the composite of two group homomorphisms is a group homomorphism. Composite of two continuous maps is a continuous map. So composite of two maps which are both group homomorphisms and continuous maps is both a group homomorphism and a continuous map. So composite of arrows is arrows. Identity arrow. Show that the identity arrow is also continuous group homomorphism, and show that composite is associative, which of course it is associative, and show, so this is a category. This is indeed a category. It's a trivial exercise, but it gives you opportunity to revise your definition of what is required in a category. Just verify those things. Okay, so we have made it a category. So now that we have category, let me ask you our usual questions. Question. What is an initial object in top? Yeah, any answer?
Probably
The trivial group.
Trivial group, and there's only one topology possible. Okay, so indeed that's okay. You have correctly answered it, and so that is the trivial group. E. You want me to write in some laborious way as E and blah 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 blah? I'll simply call it E. Okay. What is a terminal object?
That is also trivial.
Same one. Okay. How many initial objects are there? Plenty. There are so many different singleton sets. But they are unique up to unique isomorphism. See? They are not physically unique. They are unique up to unique isomorphism. Similarly, terminal object, unique up to unique isomorphism. So you see, topological groups is pretty different from topological spaces, because in topological spaces, the initial object was empty set. Terminal object was singleton one. Here, both initial and terminal are like group. Okay, next. Is there a binary product? Okay, now I'm getting tired of the notation, so we will write G dot T simply as G, usual. Okay, from now onwards, unless on the same G we are putting two different topologies or two different group operations, so we have to distinguish. So is there a binary product, which means G cross H, both are topical groups, P1 going to G, P2 going to H, with the usual universal property that given any other topological group and one continuous homomorphism here, one continuous group homomorphism here, there is a unique continuous in this comment. So what's your guess? What should we take as G cross H?
Direct product with product topology.
Absolutely. So you guys are answering very well. You see, this is a very natural answer and it works. So verify that direct product of groups with product topology and the set theoretic projections P1 and P2 works. So I'm going to call it exercise. See, whenever I tell you something and I don't write it to the last detail, that is an exercise. Everything, all self-learning, your main exercise is self-learning, you see. Don't think of exercises as puzzles. Those puzzles are a different kind of exercise. That's for the math Olympiad. Your main exercise all the time, day in, day out, morning, evening, afternoon, middle of the night when you wake up, your main exercise is to understand fully in all detail whatever you are trying to understand. That's the exercise. Learning is your main exercise. There doesn't need to be any other puzzle kind of exercises. Learning is your chief exercise. Sometimes you can have fun by answering some puzzle question. Okay, so you have been given plenty of exercise all the time because I am not writing a textbook with all details in my class. So there's lots and lots of exercises. So there's no reason for any tutorial to end before it's 1 hour. 1 hour is not enough for verifying all those things. Okay, now. So there is binary product. So next, coproduct, binary coproduct. So given two such things, I want G, H, and I have to add a new page clearly. I want from G to and I want to give a topology. So this I am not going to address. This I will leave. I will skip this. Those of you interested in investigating this, treat it as an exercise which you do after doing various other things, trying to set this up, etc., etc. Okay. Now I will come to the interesting examples of homomorphisms. So claim, exercise. Let GLNR, this is MNR, okay? This is R n square, right? With usual topology. Yeah. Bolo. Hello, somebody saying something? Please go ahead. I lost you. You guys are still there?
Yes, sir.
Yes, sir.
We can hear
But
you.
somebody said something and then stopped. So have you lost connection or you no more have a question? Which area? Okay. So take this MNR. Now you may ask, how do I make it into Rn square? Choose some order, I don't care. It doesn't have to be a linear order after all. This is a product of n square copies. Product of n square copies of R. The copies are indexed by I comma j, where 1 less than equal to R less than equal to n and 1 less than equal to j less than equal to n. Okay, the matrix entries are the coordinates of this Rn square, the n square coordinates. Now, 1. Show, so what does this consist of? Set of all x such that determinant of x not equal to 0. This easy definition is possible because R is a field, otherwise we would have to say that determinant of x is invertible. Okay, so exercise 1. Show that determinant from MNR to R is a continuous function. Can anybody quickly say why this is continuous?
Yeah, can you, sir?
It's a polynomial in, it's like
It's a polynomial in the entries, right? And what are the entries? Entries are the projections.
Yes, sir.
This is a product of n square copies of R. So there are a hell of a lot projections. There is a projection Pij going to R. This takes a matrix X and sends it to the ijth entry of X. So all these being projections, they are continuous. Yeah. Now, sum of continuous functions is continuous, product of continuous functions is continuous. So polynomial in these entries is continuous by that same repeated argument that we did earlier. So determinant is a continuous function. 2. Show GLNR is open. What's the solution?
Because
F
it's
inverse
the
0.
inverse image of
Correct.
R minus 0.
Correct. Both of you, two voices explained, one voice explained this is open, other explained the complement is closed. So great. So this is open. Now, give GLNR the subspace topology. Okay. Show it is subspace topology and matrix multiplication. Show it is a topological group. So to approach this, first you show that MNR to MNR. So I should say MNR cross MNR. MNR matrix multiplication x comma y goes to xy is continuous. So this is the exercise which said that if f from x to y is continuous and g from z to w is continuous, then f cross g from x cross y to z cross w is continuous. It is that exercise applied repeatedly will give you this. Okay, clear? So matrix multiplication is going to be continuous.
Hello,
By the
sir.
way, I'm very sorry, there's some repair work in the neighborhood with lot of banging. Can you hear me and hear the banging?
Yes, sir.
Yes, sir.
Both, you can hear both me and banging, no?
Yeah.
Very sorry about the banging, but I hope my voice is still clear.
Yes, sir.
Okay,
Yes,
all
sir.
right. So sorry about the banging. Yeah, bolo.
Sir, does GLNR has the same topology of Rn square star and dot
Not what do you mean star? Rn square, it's an open subset of
puncture?
Rn. Puncture, no, whole set is taken out. Everything with determinant 0 is removed. Now there are lots of matrices which have determinant 0.
Oh,
Ah. Okay.
Sir, I have a
So-
question.
Yeah,
When you're getting the topology on MNR,
right.
if you get it via a linear map, then it's independent of the map. But otherwise, I don't know if it is. So how can you ask when you're saying give it the subspace topology? What
Right.
topology are you giving MNR?
Mn are the product topology. I told you it's a product of n square copies of R indexed by
Okay.
I and J. Yeah.
Okay, all right.
Okay.
Thank you.
So show that this matrix multiplication is continuous. That is what on that we based all these further things, no? That all these projections are continuous. Therefore, a polynomial in them is continuous. Yeah. Yeah, Ishan.
Yeah, yeah.
It began with
Yeah,
those things being projections. No. Okay.
Hmm.
All right. Now, so matrix multiplication is continuous, and once matrix multiplication is continuous, and you know that inside this is GLN cross GLN, and you know that determinant of xy is determinant x times determinant y. So this shows that the image of this map lands inside here. Okay. So when this sits inside there and the image of this lands inside here, and therefore continuous by the universal property of an embedding. This is an embedding, right? We took an injection and gave it the subspace topology. Therefore, once some map factors through it, the factoring map is continuous. Yeah. So we are repeatedly using everything that we did in the last 2 or 3 lectures. Okay. So multiplication is continuous. But now how about inverse? 4. Show GLN to GLN, x goes to x inverse is continuous. So anybody willing to tell me how this is done? Bolo.
Probably the same subspace and factored in kind of thing, because it's
There is no inverse defined on all of M and R.
okay.
You see?
Yes, yes, yeah, yeah,
So
yeah.
not the same thing.
Yeah, yeah, yeah. I'm wrong.
So Bolo, you have to know a bit of how a matrix is inverted, na? Surely you know. How is a matrix inverted?
You mean the 1 over
Adjoint of a
determinant? Kind of?
Absolutely, absolutely. Adjoint matrix of A, okay, divided by determinant, right? Isn't that so? You know this much linear algebra, no? From your 12th standard,
Yeah,
how
yeah.
to invert the matrix.
yes, sir.
So how is the adjoint matrix made? So you want its ijth entry. So you take ij, whatever, and remove them and take rest of the entries and take its determinant. And those are going to be the entries of the adjoint matrix, or probably the transpose of the adjoint matrix. And then you multiply it by 1 upon determinant. So now, here are the steps. Each Pij from Mn into R is continuous. The ijth entry is continuous. Those are projections. Therefore, and from this, through addition, multiplications are continuous, etc., etc. Begin with this and show that x goes to adjoint x is continuous. Because each entry is continuous, therefore the determinant in these entries is continuous. Therefore, a matrix made of these entries is continuous, etc. Again, the same properties. Again and again, we are using the argument about x cross z to y cross w is continuous. That argument repeatedly used. All the previous arguments repeatedly used. Next, because x goes to determinant of x is continuous, and x goes to 1 upon x is continuous. Now, this belongs to R star. This belongs to Mn. And from R star to R star, this is a continuous map. And composite of continuous maps is continuous. We are in a category. So that goes to 1 upon determinant x is continuous. Okay. So adjoint is continuous, 1 upon determinant x is continuous, and product is continuous. This product is really product of each entry by this. Okay. And so putting all this together, inverse is continuous. So we have shown that. So what is the exercise? So assignment, write a detailed proof that GLN is a topological group. Okay. I understand that you guys are supposed to do some assignments, write and submit something and whatnot. Apparently this goes on in some of the other subjects. So here is assignment, and I'm not going to check it. All these assignments are for your own enlightenment, because only when you write a proof in great detail, then you detect gaps in your own understanding. Okay, I could go on giving you more and more examples, but at this point I'll stop and I'll ask whether you have any questions, and I'm doing my ritual countdown. And if you have any questions so far about today's material, ask. 10, 9, 8, 7, 6, 5, 4, 3, 2, 0. Yeah, no questions. Great.
Sir,
Yeah, okay. Ask.
sir, I had one question. The question is, given a group, how can we determine the smallest topology on that group such that it becomes a topological group?
But why should you be interested in such a question?
Sir, it's just a thought. I mean,
No, this is not a good thought. So,
okay, sir.
So you see, lots and lots of questions can be asked in mathematics by putting various words together, right? But there has to be a reason why you are looking for it. Why are you looking for
Because
something?
one particular reason is that in that case, I have always a discrete topology, and in that case, every group will become a topological group.
Correct.
So that is why I was thinking that.
So why don't you play with indiscrete topology and see what happens? Yeah.
Okay, sir.
Huh? Play with indiscrete topology. But the nice thing about discrete topology is, see, indiscrete will also make it a topological group. Try giving the indiscrete topology, you'll see it's a topological group, no problem. Yeah?
Yes.
But there is a certain reason for giving discrete topology, as will be clear, because then you don't have to bother about continuity of anything. With indiscrete, very few maps to other things are continuous. From here into other things, you are really putting all those points to you cannot separate them out. You're putting them all together. You want to distinguish between elements of an abstract group, right? When you have an abstract group in mind, all those elements are very different from each other. So when you make a topological space, they should all look far apart. That's why one should give it a discrete topology. It's more natural. Okay, all right. But anyway, it's not bad asking. I'm not saying you shouldn't ask this question, but also understand that questions have to be well motivated, and for a question, this kind of question, you have to experiment yourself and see that indiscrete, yeah, that's also okay, etc. Okay, all right. Now, why do we do topological groups? Because topology helps us understand the group structure. Topology even helps us understand the group structure. This is the point, as you will realize later. I am not directly going to launch into that. That requires us to go a bit hard. But let me give you some more topological groups. S1 equal to set of all Z belonging to C, says that. So mod Z equal to 1 is a topological group. As a topological group, it's called U1, unitary group, first unitary group. Okay. What's the operation? Z times W product. What is the topology? This is the topology where S sits in C, which is homeomorphic to R2. So that's the topology. So can you verify this is a topological group? I am sure you can. But verify, which means exercise. Verify S1 is a topological group. So these were all very fundamental definitional examples and exercises. Now I'm going to give you an example which is again most fundamental, but it will require you to exercise some of your mathematical knowledge. So exercise.
Sir,
Yeah.
you said you wrote that S1 contained in C is homeomorphic to R2.
C is homeomorphic to R2. Yeah, any doubts?
C is, yes. I thought, yeah, it's all right.
Yeah, okay. You, all right. You thought whether S1 is homeomorphic to R2. Okay.
Yeah, okay.
Yeah. So now I'll ask you very simple exercise. What are all the arrows in top group from R, which means R plus, to R plus? Usual topology. Huh? Now, what are all the arrows from R plus to R plus? Somebody willing to give a guess? Give a continuous homomorphism from the additive group to itself. Bolo, what will it be?
Some multiplication by scalar, non-zero.
Why non-zero?
Yeah, zero also is a group homomorphism, yes.
So one kind of example, let some constant belong to R and define the map x goes to Cx. Then what happens? Is this is continuous?
Yes, sir.
And it's additive?
Yes, sir.
Because C times x plus y, Cx plus Cy. Okay, this is an example. Is there anything else?
Probably not. No, I don't think there are any other.
Prove your answer.
Yes, because you can this homomorphism.
Exercise.
Oh, okay,
Prove
sorry,
your
sir.
answer. You have to prove your answer. Huh? Whatever your answer is, you are saying there are no other homomorphisms. So either produce a homomorphism or prove there are none. Okay, next exercise. Exercise. Let's remove the topology. Take the abstract group R plus, meaning no topology. Or you can also call it discrete topology if you want. Huh? What are all arrows from R plus to itself? Okay. What are all the arrows to itself? Now, what's your guess, Ishan?
So, which category are you looking at?
Abstract groups, I told you.
Oh, okay, abstract groups. I think probably other than that CX, but I don't have anything in mind yet.
You know, there are uncountably many such other
Yes.
ones, yeah, which are not of the form multiplication by a constant. Plenty.
Yes, sir.
They are all discontinuous. These are the only continuous ones are this. There are other homomorphisms which are not continuous. Okay, now I'm going to give you another exercise. I'm tired of just talking topology all the time. Well, anyway, this is also topology, so let me say exercise. take the field R. Okay. What are all ring homomorphisms from R to R? What are they?
So only two. One
You
is
want them to-
identity and one is trivial. I mean,
What's the other one?
Sir, you want them to preserve one, right?
Naturally, being a ring homomorphism, all ring homomorphisms are supposed to preserve 1, 0, addition, multiplication. So, one is identity, of course. Take every point to itself. That's a ring homomorphism, identity map. Are there any other ring homomorphisms from R to R?
No, sir, there are only two.
There aren't. Yes. So, Roshni, you're right. There aren't any other, but now you have to prove it. Prove that identity R is the only one. So, continuity is automatic. So this exercise is a very, very, important exercise, or you may say illuminating exercise, because it tells you how, even though in the condition we have not put any topology, we have simply said that it should preserve addition, multiplication, 1 and 0. Such a thing will automatically turn out to be continuous. While here, it doesn't automatically turn out to be continuous. There are lots and lots of things. It only preserves addition. Once you say also multiplication and multiplicative identity are preserved, then suddenly it becomes very rigid. Okay. So with this begins the new topic. Oh no, let me give one more exercise. I should give you nice mathematical looking exercises. Find out, take topological groups R and S1, okay, which means usual topology, usual group operations. What are all the topological group homomorphisms from R to S1? Next, this exercise is truly at the very, very topological. Next one. What are all continuous homomorphisms from S1 to S1? Okay. Any guesses here? This last one is like a look into algebraic topology.
Say x going to x power
X
n.
and
You know, the coordinate you use here is Z. Always think of it as complex. Okay. This is a group of C star. Okay. So what homomorphism do you think of? Z goes where? Where will you send Z?
so Z to the power n.
And what is N? What is N? You are not yet told me.
So real number.
N, real number, won't be well defined. If I try to send Z to root Z, I don't get such a map.
It should be a natural number.
Natural numbers, what about Z goes to 1 upon Z? Is that okay? Z goes to 1 upon Z is a continuous map? How about Z goes to 1 upon Z? How about Z goes to 1 upon Z cube? Is that okay? Obviously, it's multiplicative. Z times W goes to 1 upon Z times W cube equal to 1 upon Z cube times 1 upon W cube. What's there? It's continuous, obviously, yeah? So you have to take N belongs to Z. So you have given me plenty of examples. Are these all? all. Or are there any other continuous homomorphism? Okay.
These are all, I think, sir.
Yeah, Ishan, you are right now, but give me a proof.
Because fundamental group of S1 is Z.
Yeah, therefore.
So all these maps are going to descend to maps from Z to Z, which.
No. Descend from where?
So the map which you have from
What
S1.
you have in mind, Ishan, is a diagram which looks like this. You take this, okay, and you take this. What are these? These are the covering maps which we described, that here is a circle and here it's being wound around. So this is the map which sends t to
X.
e to the power 2 pi I t, or xt as we call it. This is the exponential map. And suppose this was your whatever map f. The first thing you do is that compose this, and so now I have map here. Okay, so this is f compose x, and then you use the fact that R is simply connected and this is a covering, and therefore it will admit a lift. A unique lift which will send 0 to 0. Unique path lifting. And now that is going to be a continuous homomorphism, and this has the form T goes to CT. However, what's the kernel of this map? R going to S1, the kernel is Z. And here also the kernel is Z. So the kernel has to go to kernel, therefore C should send 1 to C, C should be in Z, therefore that is it, C belongs to Z. So if C belongs to Z, the map looks like e to the power 2 pi I t maps to e to the power 2 pi I. T is now replaced by Ct, which is equal to e to the power 2 pi I t to the power C. C belongs to Z, and that means this is Z, and so Z goes to Z to the power C. So that's why these are the only maps. Now I've said it very rapidly, and here we went out of syllabus. This uses why is there such a lift? You'll have to argue by hand, knowing the properties of exponential map, etc. You don't have to use words like covering and fundamental group and whatnot. These are very concrete maps, sine and cos. So show that first of all this will have lift and blah blah blah. So this is like real mathematics. Doing this exercise is doing real mathematics. This exercise was one of the very important facts about these things discovered by our topologists, predecessors, 100 years ago, 150 years ago, when they began the subject of topology. This exercise was a big deal and very important, and it directed their further inquiries. Okay. So now I should give you a glimpse ahead. You know, in your algebra lectures, you have talked about, you have studied abstract group acting on a set. So we will instead have topological group acting continuously on a topological space. The group is going to be a topological group. Instead of just acting on a set, it's going to act on a topological space, and the action is going to be continuous. It's going to be an action in the topological category. And now you know how useful it was studying abstract groups acting on sets. For example, you were perhaps told how to derive various properties of abstract groups by making them act on various sets, for example, on itself via conjugation and whatnot. And your silo theory and various other group theoretic simple facts came out of such group actions. So topological group acting on topological space is equally important to study the structure of topological groups. This is very, very important. So we will give examples of this, and then we will talk of quotient spaces by such actions. Okay, this is one of the things I want to address. But the other thing I want to address is the whole notion of compactness. So compactness, or as I would call it, usually combined with Hausdorffness. So here is some divergence in terminology in all these old American books that you are probably reading, which are adopted in Indian universities. Compactness and Hausdorffness are kind of separate things, right? But there should be a word for compact Hausdorff. Instead of saying compact Hausdorff, one simply calls it compact. So when I'll say compact, it means compact Hausdorff. But so as not to confuse you, I'll sometimes explicitly say compact Hausdorff. And so this property that every open cover has a finite subcover, in the absence of Hausdorffness, absence or presence, needs a name. And that's called quasi-compactness. So compactness is quasi-compactness plus Hausdorffness. Plus separatedness. What the hell? Let me call it by its appropriate name. Separatedness becomes Hausdorffness in certain situations, certain categories like the topological category. All this is very applicable to more general and categories with much more structure. Okay. So it has a relative version. Proper maps. So when I started my graduate work, I realized that one of the most basic things that we should have been taught, well, actually I didn't go to any course to learn anything, but I'm so to say MSc by sitting at home and going and writing the exam. So I actually have no exposure to MSc level lectures, neither as a student nor as a teacher. And so because I was interested in physics, but I found that to avoid the physics laboratory, I enrolled for mathematics MSc, and I spent all my time in the physics department, except on the exam day, I went to the exam hall and wrote my math exam. That's how I became MSc in mathematics. But I knew the syllabus naturally. Without that, I cannot prepare for the exam. This proper maps was the most significant omission in the MSc syllabus. And so I'm going to rectify it, and I'm going to tell you proper maps, which is the relative version of compactness. And then we'll talk of proper actions of topological groups. So all this is coming in what you may say future attractions, depending upon how fast we go and how much you understand and how much you ask. So we will stop here. Let's rapidly go through the blackboard of today's lecture, and then I'll ask if you have any questions. So this was our 11th lecture, and we talked of topological groups. We first talk of abstract groups, then we talk of topological spaces, and then we combined it together, something, a set with a group multiplication and also topology, and which were compatible with each other. This compatibility meant these two maps, which are the important maps involved. The other important map in defining a group is the identity, but that's being constant is always continuous. Sending all of G to E, that's of course continuous, or sending E into G is of course continuous. So I don't have to say anything, but the product is continuous and the inverse is continuous. And then we started giving examples of topological groups. So our examples were very, very natural ones, but first of all, we made any abstract group into a topological group by just saying take discrete topology. Then R with usual topology. One of you gave this example and we verified that this is indeed okay. Then we talked about multiplicative R, and that was also okay. And here's where we used all the earlier developed technology and earlier exercises of addition, multiplication being continuous, and all the factoring and products and predictions and universal properties and whatnot. Everything went into these verifications. So we introduced this category of topological groups where the map is both a group homomorphism and continuous map together. And then we said there is a binary product, and I left all discussion of coproduct, but we will focus on product. Okay. Then we talked of GLN. One of you gave this example GLN, so we decided to verify it in great detail. So matrices we regarded as a product of n square copies of R, and the various coordinates in the matrix are the projections of the matrix on R. And then determinant is a polynomial in those, and determinant is non-zero means 1 upon that is also continuous, and all such maps factor through the universal property of subspace. Using that, we use determinant is that GLN matrix product is continuous here, and then we had to show the inverse is continuous. So we analyze the inverse as transpose of the cofactor divided by determinant, whatever your definite construction of matrix inverse is given in your linear algebra course. That involves making polynomials and making a matrix out of them, and then dividing by another polynomial, which is determinant x, and this is non-zero, so 1 upon that is continuous. All that went into showing that GLN to GLN x to x inverse is continuous, and so it is a topological group, and the assignment was to write a detailed proof. Then we talked about the group S1, the unitary group U1, which is a subgroup of the multiplicative group of C, consisting of all Z with mod Z equal to 1, and the group operation is product. Exercise was this a topological group. Then we played with these two groups, R plus and S1 with product. And so we asked what are all the arrows from R plus to itself. And then instead of group, we changed ourselves to a ring and asked what are all ring homomorphisms. Anyway, then we removed the topology and asked what are abstract group homomorphisms from R plus to itself. And I told you the hell of a lot of other ones. Find out. You just need some linear algebra to find those. Okay. The hint is regard R as a vector space over Q. And it's a vector space of some uncountable dimension. And now what are the linear maps of this vector space to itself? There are a whole lot of them. On each basis vector, you can do whatever you want. Okay. Now here continuity is automatic was what you are supposed to do. And then I asked you what are all group topological group homomorphisms from R to S1, what are all from S1 to S1, and this S1 to S1 we answered here, etc. And then I told you we are going to study action of topological group on topological space acting in a continuous manner, just as earlier you studied abstract group acting on a set. And we will study the quotient spaces by such action. And then I said made some remarks about compactness and its possible relative version, that's called proper maps. And I told you we are going to study that in coming days, and that's it. I'm going to stop.